right, good morning. There we go. So good morning and welcome to my friend's house in Atlanta. Let me fix that for you. There we go. Okay. So, sorry I was a couple minutes late here. Hopefully you guys are having a good morning in Baton Rouge. And I hope you enjoyed the guest lecture on Tuesday. So I've been in Atlanta to give a talk, a research talk, so I've figured it would be a good time to give you kind of a guest lecture from my graduate student, give him some practice, and then teach remotely here before I came back because I gave my talk yesterday and I wouldn't really be able to get back in time to lecture. So if you're here and you can hear me, things are going okay, please say hi in the chat. I see there's a few people on now. So if you don't mind. Thanks, Matt. Good morning. Sound okay? Hopefully you don't hear my wife and our friends in the other room. Okay, so today I want to talk about membranes. Last time we started working on membranes, but didn't really get to kind of much of the computational side. We did a practice problem, but it was kind of a basic mass balance where sort of by logic you could deduce, okay, how much of these algae cells was the example were removed if we had 80% removal, what would be our final concentration be? So I want to kind of pick up there and start defining a few terms and really get into kind of the math of how we can deal with membranes and look at the rejection versus the different parameters. So how does the transmembrane pressure affect the flux and things like that. So that's what we're going to look at today. Perhaps on Tuesday I will go a little bit further, but I think we'll probably go ahead and switch topics at that point. Tuesday is also the deadline for midterm grades for me to report. So I'm aiming to have all of your graded content posted for you by then. So that means I'll be catching up with the participation scores we've done, grade your exams, and your first homework. It's a little ambitious, but I'll make sure to at least get your exams done. Okay, so for membranes, a lot of times what we're going to talk about is kind of a solute balance, meaning we want to know how much of our solute is rejected from our membrane and really track what fraction removal do we have. So I want to talk about the fraction rejected here, what we're going to call R. So if R is our fraction rejected, then we can describe that as 1 minus the concentration in our permeate. So if we had, let's say, a membrane, we'll draw kind of the box diagram here. We have a membrane, water coming in, water leaving, and some water rejected. So typically we'll have a Q feed and a concentration feed. And then when we talk about permeate, that's whatever passed through that membrane. So that would be our QP times CP. So this is what we're talking about when we're talking CP over CF. So what concentration made it through versus how much we are feeding to the membrane. So that's 1 minus that. So that ratio is the ratio that permeated through. So 1 minus the ratio that permeated through is the ratio that's rejected, or the fraction rejected. We can also consider this in a log value, where we would say our log, so the log fraction rejected, would be the log of CF over CP. So let's take an example to work through that to make sense of why it's, in this case for the log, it's the CF over CP. So we kind of reverse that. So in the problem last time we did algae removal, we did something like 80 or 90%. Let's say we have 99.99% algae removed and look at what that means mathematically. So in a continuous flow system. So if we were to just take the fraction rejected, that would be 1 minus 1 over 10,000. And that 1 over 10,000, that's just a fraction that represents, 0.01%. So that if we had this much removed, that means we have 0.01% remaining. And that would be in our permeate flow. So that would be our CF, or CP, sorry. Okay, so if we have this R value as 1 minus that, we get an answer of 0.9999. So that's, very simply, we could have just taken this 99.9% and said, oh, let's move the decimal place, and that's our fraction, right? It's kind of given. But that's not always very convenient to write it that way or to say it that way. And so sometimes we'll use this log removal, again, like we do often in our disinfection. So that our log then would be the log of this 10,000 over 1. And that equals 4, because the log of something, when we set up log of x equals y, that's saying the base log base 10, for example, log base 10 of x equals y. That means 10 to the y equals x, right? So that's our solution. That gives us the 10 to the 4th equals 10,000. And so we can just say that's a 4 log removal because we removed the 99.9% or 99%. Okay, so that's just kind of the log scale system at play again here. Nothing particularly fancy or tricky there. And I will give you these equations just so you have them as a reference. Really what we're dealing with is ways to talk about the ratios between the amount of stuff in our solute versus in our in our feed compared to what's permeating through the membrane. Okay, we can also take a look at the water balance. And so here, what we're talking about is how much water are we using in our process. And if we want to know, perhaps we have some specified amount of rejection that we need and we're achieving that. But then the next question is, okay, well, how much water are we actually getting out of the process? Are we wasting 10 gallons for every 1 gallon produced? Or are we getting, 99 gallons when we fed to the membrane 100 gallons? That's a big difference. And so the way we talk about the water balance is a recovery rate, and that's a lowercase r. I do apologize, there's lots of r's. I'm keeping consistent with one of the books I posted as supplemental materials. I can help you find and look at that if you need, but you can check our syllabus. There should be some recommended books, one of which is, or several of which are available online. So I'm trying to keep consistent with some common nomenclature for that. Our primary book does not have a lot of information on membranes, just a kind of a brief section. So I've taken some problems and some material from another book. Okay, so this water balance, the water recovery rate, lowercase r, this is going to be the fraction of the amount of flow in the permeate compared to the amount of flow in our feed. So this is essentially, we'll say permeate flow divided by the feed flow. And we can get that, we could also say that's going to be the QF minus the Q that we reject divided by QF. So in some sense, it's, that efficiency term, we started with some amount of water, we rejected some of it, and that went to waste. And so what portion do we get out of this as kind of an efficiency sort of a deal? And this would come directly from the fact that we have a flow balance here with our feed, our retentate stream or rejected stream, and our permeate stream. Okay. Another quick example would be if we had a membrane that treats 100 liters of water, 15% of it goes to waste, then our R value, that water recovery rate, is 0.85 because 85% of the water is recovered as usable clean water. So that's kind of the system there. Okay, so the next concept would be flux, and we dealt with flux a bit in a sort of a different way when we covered granular filtration. We'd have some filtration bed, and we said, okay, well, water's going to go through. We have some length and width, and so as water is being poured through, we have the surface area, and it's essentially a flow rate divided by a surface area. It gives us, in the granular filtration case, we called that a loading rate, because that's the rate at which we're loading water onto the filter. In membranes, we'll just call that a flux. Both are technically fluxes, we just used a different term for it earlier, but a flux is an amount of stuff going through some area. All right, so a lot of times we'll use units like liters per square meter per hour. The volume term here, of course we could use cubic meters, but it will fairly often be just simply liters. The square meters here will pretty certainly be an area unit. So meters squared, feet squared, centimeters squared, something. Most often meters squared. And then time will be, whatever is convenient or fitting for the problem. Okay, so like I said, this J here, this is going to be the Q in the permeate, by the way. So this is not the Q that we're feeding to the membrane. So if we take a kind of a side view again, or a box diagram view of a membrane system, we have our feed, we have a membrane. Let's draw that a little better. So we have our membrane, we have our permeate, and we have our rejected. So when we talk about flux, this is flux across a plane, right? So across the membrane. That word across is very important, because what we're talking about is the flux that makes it from one side to the other. So we might be tempted to calculate flux as Q in the feed divided by the area, but that would be wrong. Okay, so it's not QF, it's QP. Okay. So let's do a problem, and I'll give you a couple minutes to work on this before I solve it with you. This is from one of those books online. It's example 12.1. We have a comparison of an outside in and an inside out filtration setup. And this actually calls back to something I mentioned last time about doing tubular filtration and doing the inside out versus outside in. Okay, so a Dow FilmTech SFX 2860 membrane module contains 5,760 fibers. The fibers are 1.87 meters long with an outside diameter of 1.3 millimeters and an inside diameter of 0.7 millimeters. Calculate the water production from one module if the flux is 75 liters per square meter per hour. And the flow direction is 1 outside in or 2 inside out. And then compare the two answers. Okay, so I'm going to take a moment as you start thinking about the problem to kind of sketch out just a couple of thoughts here. First of all, what we're being asked for is two answers. So it says calculate the water production from one module if we have that flux and if the flow direction is inside out or outside in. So the water production, calculate the water production. The first thing you may be thinking is, what does that mean? Calculate the water production. You know, you could for a moment think to yourself, well, this is going to be some volume, right? Water production, we're producing some volume. That's a reasonable thought, but you're not given a certain amount of time. So given that it's not like water production per day or not water production in an hour, you probably need a flow rate instead of a volume here. So that water production, I think the best way to interpret that would be QP. That's the question. So we'll leave a blank there and a blank here. Next thing, hopefully you're starting to do is think about drawing a diagram for the two cases. So I'm going to do that, and then I will let you work on it for a few minutes. So I just saw an email from Anne. If you're able to see it now, if it's working now, please let me know. I'm about to email you back. Okay. So if Anne, if you're on the live stream, please see if you can chat to say hello. Okay. If that's enough time, hopefully it is. We'll go ahead and work through that. So the problem here is really about finding the membrane surface area and then using that to calculate the flux. So again, our flux ultimately is going to be Q over AB. And this is going to be our, sorry, not AB, Q over A filter. Our flux is actually given at 75 liters per square meter. So we're going to say that's going to be equal to QP over A, or we can say that our QP will equal, based on that, we can say QP is going to be equal to 75 liters per square meter times this the area that we calculate. And I missed an hour here. So the flux is liters per square meter per hour. So we need per hour there. Okay. So the problem then becomes, okay, good. So then the problem becomes a simple matter of solving for that area, and then we have the flow rates there, or the flux there, and we can calculate that flow rate. Now then, this is a geometry problem for essentially a cylinder. So when I made my drawings, we were talking about these hollow fibers. So we have these long, thin cylinders that are hollow, and we need to calculate the surface area of that based on where the water is going to cross and essentially experience filtration. And so that's either going to be on the first case, since the water is flowing from the outside boundary of this membrane is going to be our surface, right? It's kind of poorly drawn there, but you get the picture. So the outer portion is going to be what we calculate the surface area for. For the second condition, the inside diameter is going to be that separation layer, the one where we need to calculate. So based on that distinction, we have one of two surface areas. So our surface area generically is going to be equal to the length times, so that's the length of the fiber, times the circumference. And who knows if I spelled that right. So the surface area then becomes the length times pi, 2 pi r, right, is the formula for the circumference of a circle. Or we have that in diameter, so we'll just go ahead and say that's length times diameter times pi. Of course, we're going to need to get like units, so we need to convert the lengths from millimeters into meters. So that's 0.0013 or 0.0007 meters. And we put those numbers in and then solve. So that is rather simple, and I'm going to go ahead and bring over this Excel sheet here to show kind of what's going on. The last thing you're going to need to know, in addition, instead of just using that one surface area, that was the surface area for one fiber. So then we need to multiply it by the total number of fibers, which was 5,760. So what I did then was I said, okay, we have the length, 1.87 meters. We have a diameter, convert that from millimeters into meters. And then I said, okay, well, the area for one fiber is going to be equal to the length, the length of the fiber times the diameter of the fiber times pi. So exactly our derivation right there. And so that turns out to be 0.007637 square meters for the area of one fiber in the first case. And then the only thing we left to do is to multiply that by the number of fibers to get our total surface area for that system. So that gives us our area of the module for case 1. We also need the water production, so we'll calculate that. This is going to be equal to this times that 75 liters per square meter per hour. So that gives us liters per hour. So the flow rate in case 1 is basically 3,300 liters per hour. When we do that for the second case, our flow rate is smaller because we're using the inner diameter and we have less surface area to work with. And so we have that flow at 1776.5 liters per hour. Okay, does that make sense? Any questions? You should be able to put a chat message if you might not be showing if you're in full screen mode, but if you do ever have a question, you should be able to type a question into the chat and then see it pop up on the feed. So if anybody else asks a question, they'll be able to see what you're asking and what I'm answering. And then that feed will disappear in a few minutes. So if that's not working for you, then you might have to log in or create an account or something. Should be relatively straightforward to do so. And then, yeah. But do let me know. If you're having trouble with that, you can email me. I'll check again in a few minutes. Okay, so let's go ahead and I guess put these answers here. For this one, we said that was approximately 3,300 liters per hour. And the other one I think was 1776 liters per hour, or very close to that. Okay, so let's talk for a minute about the pressure. And really the pressure is our driving force to achieve the filtration, to kind of push the water through, or in some cases if we're doing reduced pressure, then to pull the water through. We're going to call this a transmembrane pressure. So essentially the membrane pressure that, oops, one second, adjust this. Okay, so essentially this is the pressure that crosses the barrier. So the pressure drop or the pressure change across the membrane barrier is what we're referring to here. And so this is going to be the pressure. We can measure it if we were to measure the pressure in the feed and subtract from that the pressure in the permeate. So this equation here, if we have a membrane, and we can do this in one of two ways. We could apply a negative pressure, so a vacuum, on this side, or, so let's say a vacuum over here, or an increase in pressure over here. Either way, that'll push water across the membrane. And so if we measure that right up next to the membrane on either side, that gives us a very accurate view. But you can also usually just measure it in the flow, in the stream, in the water. You put a pressure meter here and a pressure meter here, and you'll be okay. Okay, so there's a bit more complexity to that for, defining specifically pressure, maybe inside the membrane. There's some highly technical stuff you could get into. We're not going to get into it. We're just going to say that you can apply pressure on the front or apply a vacuum on the back, or you could even do both. And then you'll be set to go. Okay, so then we are going to define the transmembrane pressure typically in pascals. So we'll use the feed pressure in pascals and the permeate pressure in pascals, so PF and PP. And the way these relate to flux are essentially that the flux is equal to that pressure, the transmembrane pressure, TMP, divided by a total resistance of the membrane times the dynamic viscosity of water. So if we think about resistance, we have some sort of a membrane. Water is trying to go across, and we have our pressure in the feed and a pressure in the permeate driving that gradient. But then if inside this membrane it's really tightly packed with no space for water to go through hardly at all, and water has to really travel through lots of little pores, and it's slow going, you can see how the pressure is going to be forcing it across, but then you're going to divide that by how much resistance is in the way. So even if you have a lot of pressure, if you have an enormous resistance, then you're going to have some problem. And then you also have this viscosity factor, this how sticky is the water, essentially, or the fluid that you're filtering. You can imagine trying to pressurize honey through a membrane. It's going to be quite difficult because it's so viscous. So let's take a quick look at these terms. If the flux is defined by that pressure divided by this resistance and mu, well, let's take a look at the units for the resistance. That is per meter. So resistance is a per distance unit. So essentially, the farther you have to go, the more, essentially it's a metric of how difficult per distance. So this will also relate to the fact that we try to design our membranes so that the separation layer is very thin, so that the really important filtration part is just almost one little layer, and that gives us less resistance total to deal against, essentially. So the units here, we have a volume per area per time for a flux, and in terms of the pressure in pascals, that's relating to newtons and square meters, and we're dividing this by